Bueno,
Recording in play in progress.
so,
Recording in progress.
bueno, good morning, everybody. Welcome to the first session of the Seminario Internacional de Matemática. I'm honored to introduce my colleague and good friend Melody Alsaker. So Melody has a PhD at Colorado State University, and she is an specialist in medical images, in application of mathematics in medical images. So she gonna introduce today in her talk some of her latest topics of her research. So it is a pleasure, Melody. You are the first speaker. Having not Spanish as the primary language, so that's the intention of the seminar. We are really, really happy to have you today in our seminar. So, as always, please shut down your video and mute. Without anything else to say about it, I'll leave you with Dr. Alsaker. Go ahead, Melody, please.
All right. Thank you, Tomas, for that wonderful introduction. And I'm going to go ahead and try a screen share here. And actually here, let's just do this because that way I end up showing one of the videos I have. We can run that also. All right. So yes, we're going to talk about electrical impedance tomography today. Which is my specialty in my area of research. And I am aware that I think a lot of people in here are probably pure mathematicians, algebraists, not applied mathematicians. So this is going to be very much a talk for general mathematical audiences. I tried to keep it fairly low level so that not leaving anybody in the dust, hopefully. And so, yes, my area of research is computational medical imaging. And so I've worked with a number of imaging modalities and different types of medical images over the years. And in particular, now medical imaging always involves what's known as an inverse problem. And before we start talking about electrical impedance tomography in particular, I would like to talk a little bit about the background of what an inverse problem is, because it helps understand some of the challenges in electrical impedance tomography and medical imaging in general, if you know a little bit about what an inverse problem is. And inverse problems show up in all sorts of real world problems, not just medical imaging. So they are a very highly active area of research in applied mathematics right now. So yeah, what is an inverse problem? Let's take a look at that to start with. So every inverse problem has a corresponding forward problem, and it's usually a little easier to understand the forward problem. And once you understand the forward problem, then it's pretty straightforward to understand what the inverse problem is going to be that goes with that forward problem. So here's the simplest possible example that everybody should be able to understand. So a forward problem is we know the inputs to a process and we wish to determine the outcome of that process. So multiplication of two positive integers is a forward problem. So we have 6 and 7 as our inputs, and we perform multiplication and we get an answer 42. All right, that's straightforward. Now the inverse problem that goes with that, an inverse problem is when we know the outcome of a process and we wish to determine the inputs. So the inverse multiplication problem is, if we know what the result was, we know the answer is 42, but what two numbers did we multiply, right? And if you limit yourself just to positive integers, here's some possible answers. And so importantly, the solution to the inverse multiplication problem is not unique. So we can already see there's something less nice about the inverse version of this very simple problem. And that's kind of a theme in inverse problems. Inverse problems are just not as nice. They're harder problems than their forward problems. And of course, another simple example that we're all familiar with, a forward problem is differentiation. So you have a function, you take its derivative. The inverse problem is indefinite integration or anti-differentiation. And we all know that when you take the indefinite integral of a function, you get this plus c on the end because the answer is not unique, right? Again, we don't have that uniqueness that we have with the forward problem. So it's less nice somehow. It's a harder problem. And here's another example where the inverse problem has a different kind of not niceness associated to it. So a forward problem is matrix multiplication. So if you have a matrix and a vector, you can multiply them, you get some vector as an answer. The inverse problem is if you know that result vector, the B, and that original matrix A, can you figure out which vector X was multiplied to get that answer? And the issue with this inverse problem is that the solution may not exist, right? You can't just take any matrix A and any vector B and expect there to be an answer because, you know, that A inverse matrix might not be, might not exist. It might be singular. So again, we have this situation where the inverse problem is just not quite as simple. And so inverse problems occur in many, many physical applications, and this is always when an effect is known, but we wish to kind of go backwards, follow the paper trail backwards and discover the cause of that effect that we're observing. And they're almost always more difficult than the corresponding forward problem. The forward problem would be if we knew the inputs and we knew the process and we just want to figure out what the output is. And so why is this? And it's because inverse problems are ill-posed. And in fact, this is considered one of the main characterizing features of any inverse problem is its ill-posedness. You know, how ill-posed is it? And what can we do about that? So in case you don't know what ill-posedness is, it helps to know what the definition of a well-posed problem is, and then an ill-posed problem is just one that's not well-posed. So a well-posed problem, as defined by mathematician Jacques Hadamard, you have to meet all three of these criteria. So your problem has to have a solution. Number one, a solution needs to exist. The solution needs to be unique, and the solution needs to be continuously dependent on the initial data so that small changes in the initial data and the inputs to the problem lead to correspondingly small changes in the outputs. And the fact is that most inverse problems fail to satisfy at least one of these conditions. So in those very simple examples we saw, they were failing one of these first two criteria. In more complicated inverse problems like medical imaging, for example, it's very often this third one that's not satisfied, where we don't have this continuous dependence on the input data, and that causes problems. So we're going to go through a few very simple, well, increasingly complicated, I should say, examples of real world inverse problems. These are things that are active areas of research. So the image deblurring problem, as simple as this problem seems at first glance, you know, what you want to do is you have a blurry image and you want to go backwards and recover, you know, what was the sharp image, the input that went into that. And so it's very easy to take a sharp image and you apply a convolution filter and you make it blurry. But once you've got that blurry image, you know, can you ever really recover exactly what that sharp image was. And I think even for those of you who know nothing about image processing, who are, don't work with inverse problems, I think intuitively you're going to say, yeah, there's something wrong with that, right? That, like, you've lost some information. There's some information that's just fundamentally gone from the system when you blur this image, and you're never going to be able to exactly recover the sharpened image. So this problem, which is sometimes known as the 2D deconvolution problem, also because going this way is a convolution operation, so going this way is a deconvolution. People are still working on this problem, trying to make better sharpening filters so that we can, get rid of blurry images and see features in them. But yeah, nobody is ever going to be able to perfectly recover the original, because that information is just gone. The detection of extrasolar planets is an inverse problem, and this one's pretty cool. So this is not related to medical imaging as much as some of the other things we're going to talk about, but it's something that's shown up in the news lately because they recently just detected the first extragalactic planet, meaning a planet that is outside of the Milky Way galaxy. And so how do they do this? Well, the idea is that if a planet is orbiting a star, then the planet's gravity causes that star to wobble, okay? And this wobble is observed in a Doppler shift in the wavelength of light. So as the planet moves, or as the star, I should say, as the star moves away from us, we see a red shift where the wavelength of the light shifts into the red end of the spectrum. And as the star moves towards us, it shifts into the blue end of the spectrum. And we can measure those shifts, those Doppler shifts, in the magnitude of those. And so from those measurements, can we determine the orbital radius and mass of that planet that we can't see? We cannot see the planet directly, right? So we've got telescopes that can maybe see the star because it's bright, but the planet is just simply too dim. So it's these indirect measurements that are giving us information about this object here. And yeah, this is an inverse problem. Are you going to be able to ever recover the orbital radius and mass exactly? Yeah, probably not, right? And I think most of you, again, even if you don't know anything about this problem, you can say, like, from just an intuitive standpoint, like, no, there's going to be measurement noise, and you're not going to be able to exactly recover those measurements. So on to an actual medical imaging procedure here now. So X-ray imaging is the simplest type of medical imaging that we have, aside from just taking a photograph. I guess you could take a photograph, like a microscope slide photo, and that would be a very, very simple medical imaging procedure as well. So this is like the second simplest. So in X-ray imaging, the input is an object with some kind of internal structure, maybe a person. And the process is that we shoot X-ray beams through that object. And of course, the beams just pass linearly through the object. And they hit this detector plate on the other side. And any beam that passed through the object is partially absorbed or attenuated by that object. So the outputs are the beam intensities that are measured on this detector plate over here. And so given that the measurements of the beam intensity, can we recover the internal density of the object? So when you see an X-ray image, what you're really seeing is a density map of the internal structure. And of course, it's been projected flat, right? We have a 3D object and it's been projected into 2 dimensions. But X-ray is actually, we get pretty sharp images considering how simple this process is. And so that's why it's stuck around. We've had this technology for a very long time, and it's not going anywhere because even though it's so simple, we really get pretty nice images from it. here is one that's a little more complicated, but it's really cool. I like to talk about positron emission tomography because it's just a really interesting one. So in PET scans, it has to be a living object for this to work. You can't do a PET scan of, you know, a rock or something like that. So it has to be a living object because it needs a metabolism. So here we have a human head as the source of input here. And the process is we inject a radionuclide into the patient. So this is a radioactive substance. And this, you can either take a pill or you can take it by injection. And so this radioactive substance, it goes into your bloodstream, it goes all over your body, but it collects in areas of the body corresponding to high chemical activity. And so when it collects in these areas, it because it's radioactive, it undergoes radioactive decay. And through that process, it releases a positron. So a positron is released, that's an antimatter electron, basically. And so this antimatter particle almost immediately meets an electron within, like, you know, a fraction of a second. It hits an electron, and you know that matter and antimatter annihilate each other on contact. So it annihilates. And this emits a pair of gamma rays. So you can see here in the picture, here's like the point of annihilation. And then it emits this pair of gamma rays simultaneously out at 180 degrees. So here's like two possible examples. And we don't know exactly what directions these are going to go. They just go out at 180 degrees from each other. And then we have this detector array around the outside. It has a reactive substance that, you know, lights up when gamma radiation hits it. And so we can measure the fact that two of these detector I guess components have lit up at the same time. And then we can make a guess for, well, if this one and this one lit up at the exact same time, then the area of high radionuclide activity is somewhere along that line. And then if this one and this one light up simultaneously as well, then we have this intersection and we can see, well, maybe there's something going on here. So you collect all this data about these intersection points. And this is the type of image that you get from that, where here the red areas are the areas of high chemical activity and the blue areas are low chemical activity. So this is a pretty cool one. So the inverse problem here is, given measures of the gamma ray pairs, can we recover the areas of high chemical activity? Okay. Ultrasound tomography is one that I've worked with a little bit myself. And in ultrasound tomography, and this is a little bit different than, so if you've seen the fetal ultrasounds, that's what people usually think of. That's a single ultrasound transducer. So ultrasound tomography is when we put an array of ultrasound transducers all the way around an object. And so we're shooting ultrasound radiation, which is it's just sound waves, into the object from all these different directions, and so that we can get a slice image. And so this particular one here, this is a human breast. It's used for breast cancer detection. So in ultrasound tomography, we have, again, the input is some object. The process is that sound waves are applied on the surface and they propagate through that object. And then the outputs that are measured on the transducers are the resulting acoustic pressure that results from the sound waves propagating through the domain and then, you know, creating this pressure distribution back on those transducers. Okay, so you can see that's the type of image that we can get from those. Now, finally, moving on to electrical impedance tomography, which is what I work on. So again, the input is an object with some kind of internal structure. And the process is we put an array of electrodes all the way around the boundary. So tomography just means slice imaging. So again, we're recovering a slice of the domain. So we put the electrodes in hopefully something close to a plane all the way around the patient's body. And we apply electrical current. And this electric current, it propagates through the domain. And then this results in a surface voltage distribution on the domain. And so the inverse problem is given the measurements of the surface voltages, and of course we know what currents we applied to begin with, can we recover the internal conductivity of the object? So this is a conductivity map here. You can see that the heart is in red here, and then the lungs are in blue. So that is a picture of the inside of that person's body based on the internal conductivity distribution. So for those of you who don't know, conductivity, this is a measurement which quantifies how well an object conducts electricity. The SI units are in Siemens per meter, which is sometimes it's called Mohs per meter because it's ohms backwards. So this is the symbol for an ohm, right? So it's 1/ohms. So it's called a mho. I know that's kind of silly. So, you know, high conductivity objects are things like metal, right? Conducts electricity well. Graphite, salt water, blood, all conduct electricity quite well. Low conductivity things are like glass, ceramic, wood, plastic, air, you know, your insulators. Okay. And then our picture here, what we're seeing is a tank setup. So this is an experimental setup. This is a PVC tank with electrodes all the way around the outside of it. And it's filled with a saline solution. So salt water does conduct electricity. And inside the tank, we have 3 objects. 2 of them are metal and 1 of them is glass. And here is the resulting conductivity map after we reconstruct the electrical conductivity based on the boundary measurements. So we can see here the metal objects are showing up in red and the glass object is showing up in blue. Okay. And now electrical impedance tomography, it works for medical imaging purposes because human tissues have a lot of conductivity differences. So you can see that blood has a very high conductivity compared to some of these other tissues, right? And so compare that to, say, bone, which is very low. Your bones do not conduct electricity especially well. Or your lung tissue, you know, your lungs are, well, full of air, right? So when you breathe in, especially, that's what inspiration means, when you breathe in, your lungs fill up with air and the conductivity of the lungs goes way down because of all the air there. And even when your lungs are fully exhaled on expiration, the lung tissue just does not conduct electricity especially well compared to some of their surrounding tissue, the blood, and then the cardiac tissue, of course, that's the heart, has very high conductivity as well. Your skin is very resistant. So this is, you know, nature's way of protecting you from electromagnetic radiation. So unless you get your skin wet, and then it becomes more conductive because you have dissolved salts and things going on that will conduct the electricity quite well then. So, all right, moving on. Now, some advantages of electrical impedance tomography in medical imaging applications, you know, as opposed to some other imaging modalities. This includes, first of all, we don't have any ionizing radiation in EIT. So this means, you know, every time you get an X-ray scan or a CT scan or a PET scan or a bunch of these other modalities, they give you a radiation dose. And these radiation doses are cumulative. They can add up over the course of your lifetime. And it's been documented, there's been studies done that if you if you have gotten a lot of certain types of scans, like CT scans, you are at an increased risk for developing leukemia and other cancers. Okay, so there's no ionizing radiation involved in EIT. It is painless. You do not feel the electricity that's applied to your body because it's low frequency, low amplitude electrical current, so you don't feel anything at all. It is low cost, and this is a big deal because a lot of hospitals in poorer areas, rural areas, and also developing countries, they might not be able to afford some of the big fancy MRI and CT scanners. Those are very expensive machines. An MRI machine has a price tag of around $1 million US, whereas an EIT machine has a price tag of around 50 to 80,000 US dollars. So it is significantly cheaper than an MRI machine. It's also portable. So an EIT scanner can be moved to the patient's bedside. It can be put on an ambulance. It can be put on a helicopter. So you can take it into rural areas where they don't have hospitals. You can take it into war zones and use it to triage people. And you can also, for bedridden patients, patients that simply cannot be gotten out of bed, you can move the scanner to the patient instead of taking the patient to the scanner, which is often a traumatic experience for a bedridden patient. We do have functional imaging capabilities with EIT, which simply means we can watch the patient's internal bodily processes unfolding by taking a series of images and making a movie out of it. So we can see, the heart beating, or we can see the air going into the lungs. I've highlighted the real-time imaging because this is something that I have helped develop. This is an ongoing project. I'm actually involved in a collaboration with, there's a collaborator I have in Switzerland I'm working on this with right now to improve the real-time imaging capabilities, which just simply means you want to be able to collect the EIT data and reconstruct it with a very, very short delay between the data collection and the reconstruction. So you can basically watch the patient breathing, for example, in real time. And it's the technology is also suitable for use on small children without anesthesia. And this is a big deal because little kids, they can't hold still in like an MRI scanner, for example. So you have to put them under, you have to give them general anesthesia. And of course, there's a lot of risks associated with that. So you can do an EIT scan on a baby without having to anesthetize them, okay? And this won't go to the next screen for some reason. Okay, we'll just scroll. That works. And so the thing that I have been working on in particular over the years has been mostly pulmonary imaging, which means lung imaging. So these are some of the things that you can use EIT for, in particular dealing with the lungs. And so collapsed lung, blood clot in the lungs, fluid in the lungs or in the surrounding pleural tissue, ventilation monitoring. So this has been a big one, of course, with COVID. Patients who are hooked up to ventilators. I guess I'm not a technician, I've never, I've never adjusted a ventilator for a patient before, but from my understanding, adjusting the settings on a ventilator is actually more art than science right now. People who are trained to do this have to be very, very careful that they do not accidentally injure the patient by overinflating the lungs. And of course, if you underinflate the lungs, then they're just not getting enough air and they can die. So it is very advantageous to be able to see the air going in and out of the lungs. So EIT has seen a large amount of interest over the course of the pandemic because of this. And then these two in red are things that I have worked on in particular. So the lung volume measurements, meaning if you want to determine how much air a patient can contain in their lungs, you can use EIT for that. I published a paper on that a few years ago. And also monitoring air trapping in cystic fibrosis patients at Children's Hospital, Colorado is where I did that collaboration. And all right, we'll just keep scrolling here because for some reason the arrow key stopped working. So now those are all good news things for EIT, all the great things it can do, but bad news, EIT as an inverse problem, it is severely ill-posed. It is a really bad one, okay? It's a really hard inverse problem. And in particular, the thing that goes wrong, the root of all the evil is that the EIT images look blurry, right? We are never going to be able to get crystal clear, sharp images with EIT. And so the good news, though, is that this keeps mathematicians in business. So there's lots of people like me all over the world who are actively working on trying to make EIT images look better. And so, yeah, I've made a career out of it, and a lot of other people have as well. Maybe one day we'll get something that's really good, but yeah, we're just, we're working on it still, trying to make these images look better. So let's we're going to get into a little bit of the actual mathematics here now. So here is just the background. Once again, for EIT, we have a domain, omega, and inside this domain is some kind of conductivity distribution. So each one of these internal objects here, you could think about it as a heart and two lungs, if you like. And then, the surrounding tissue. Each one of these has its own conductivity associated to it. We apply an electrical current to typically 2 electrodes on the domain boundary. And this creates the electrical current propagates through the domain, and this creates a voltage distribution on all of the electrodes that can then be measured. And then we want to use that boundary data, the known electrical currents and the known boundary voltages, to reconstruct that internal conductivity distribution. Whoops, that is interesting. Here, I think, yeah, I don't know what's going on with my arrow keys, but I hit an arrow key and it went backwards like 4 slides. Okay, so we've got Maxwell's equations here. This is the base of the mathematical model. So from Maxwell's equations of electromagnetism, we can derive a mathematical model for the propagation of electromagnetic fields within, within anything, but we're thinking about within a human body here. So this is what we can derive. This is the conductivity equation. So the electrical potential here is given by the variable U, and we are in a 2D bounded domain, omega. And the sigma here in the equation, that is the conductivity that we would like to reconstruct. And for those of you who are, maybe have some PDE background, you might recognize this as a generalized Laplace equation. It's an elliptic PDE. And we can add boundary conditions corresponding to the known boundary voltages and the known boundary current densities. And the boundary voltages here correspond to what's called a Dirichlet boundary condition. These are terms from PDE theory. And then the boundary current densities correspond to what's called a Neumann boundary condition, because we know the derivative of the function U on the boundary. The mapping that takes the boundary voltages to boundary current densities. Then it maps the Dirichlet boundary conditions to the Neumann boundary conditions. This is called the Dirichlet to Neumann map. It looks like this. And so we use this big lambda here. So this represents all possible voltage to current measurements, and it's been proven that the conductivity, that's what we're trying to recover, can be uniquely determined from this mapping in a theoretical sense. If we knew the mapping exactly, which we don't, then we could exactly recover the conductivity. And in practice, we have a finite number of discrete boundary measurements corresponding to a finite number of discrete electrodes. So the DN map is a matrix computed from the voltage and current measurements. And so let's take a look here. What is our forward problem? What is our inverse problem? So the forward conductivity problem would be if we knew the internal conductivity already, and we knew the boundary voltage distribution, we would just solve this PDE for you. And this is not that hard of a problem. We could readily solve this using numerical techniques. The inverse conductivity problem, however, is given knowledge of that DN map, which contains all of the boundary information. We want to recover that parameter sigma from the conductivity equation. So this is known as a parameter identification problem. It's a whole class of inverse problems called parameter identification problems, okay? And it's a much harder problem. So I'm going to go over the basics of what we call the dbar algorithm. This is a direct solution method for EIT. It's a little bit unique. So this is what I work with. So it's a direct method as opposed to an iterative method. I would say the vast majority of people who work on EIT across the world use iterative techniques or statistical inversion techniques. So this is a little bit unique. We're going to begin with the conductivity equation and of course our measured data, which is stored in the DN map. And we define a change of variables which transforms the conductivity equation into the time-independent Schrodinger equation. So here's our change of variables. This is a Laplacian, so it's like a second derivative operator there. And so this transforms the conductivity equation into the Schrodinger equation. Yeah, like that Schrodinger equation from quantum mechanics. That's what we're working with now. So we've changed, via this change of variables, an electrostatics problem into a quantum mechanics problem. And this Q here, defined under the change of variables, we call this the Schrodinger potential. So I'll refer to that. And so the solution to the Schrodinger equation is this function psi. And then we associate the real spatial domain with the complex plane. So that points in R2 are associated to points in C. We introduce a complex frequency parameter K. And this is non-physical. It doesn't have a physical representation. You just kind of stick it in there. And we look for solution psi to the Schrodinger equation satisfying this asymptotic condition. So we want psi to be asymptotically equal to this complex exponential, e to the ikz. And solutions of this form are known as complex geometrical optics solutions. We define the scattering transform then. So this is that Schrodinger potential Q. This is the solution to the Schrodinger equation psi, and it's satisfying that asymptotic condition. So that's our CGO solution, complex geometrical optics solution. So the scattering transform is defined like this. Okay, fine. And this can be written equivalently. You go through a couple of Green's identities. You transform the integral over R2 into a boundary integral just over the domain boundary. And then you can associate the DN map. So this is your measured data here with that CGO solution to the Schrodinger equation. And so the lambda 1 here, this is just the DN map corresponding to a homogeneous conductivity distribution in the domain, which could be numerically simulated. So it's another it's like another set of data that doesn't correspond to a physical scenario aside from that. Yeah, it would be if the internal domain was just all one homogeneous material. And so this scattering transform, we can think about this as a nonlinear Fourier transform of the Schrodinger potential. And in fact, because psi is asymptotically equal to e to the ikz, you can do a little bit of algebra here and show that for large values of k and large values of z, this does actually approach the usual linear Fourier transform of the Schrodinger potential Q. And the boundary integral formulation then connects that scattering transform to the EIT data. So given a solution, a CGO solution to that Schrodinger equation, we're going to define this auxiliary function mu like this. So, you know, this function here is asymptotically equal to e to the ikz. We're multiplying it by e to the minus ikz. So mu is asymptotically equal to 1. And then we're going to recall the dbar differential operator. If you've taken a complex variables course or taught a complex variables course, you're familiar with this one. And so the dbar operator, it's just this fancy derivative operator. So we're just defining a couple things here. And so from that Schrodinger equation, we may derive that the auxiliary function mu, which is related to the solution to the Schrodinger equation, satisfies this, what we call dbar equation. And it's called the dbar equation because it's got this dbar derivative in it. So you can see the scattering data is right here. So that's where your measured data would show up. And we can write this equivalently in integral form. And in this formulation, it is a Fredholm integral of the second kind. We can solve this on a computer, basically. It's not that hard to solve this. And so if we solve this for mu, we can see here that there's actually a simple algebraic relationship between the mu and that function psi, or sorry, sigma, that is the conductivity that we're trying to recover. So we have our measured data showing up right here. We put it into this big integral equation and we solve it on a computer for that function mu, and then the mu gives us the conductivity distribution. So that is the direct method, the dbar method for solving the EIT inverse problem. And so some of the things that I've been working on, and these are things that are, you know, related to trying to improve the image quality. So the scattering transform, that is where the measured data shows up. You know, if you look back at this equation, that is the place in this equation where the DN map, the measured data, shows up. So all of our data measurements are encoded in there. So the scattering data does encode all the information necessary to reconstruct the conductivity, but it is unstable in the presence of noisy real-world measurements. So to regularize the reconstruction, and regularization just means we're pruning out kind of the bad information that is, you know, unstable due to the noise, and we're keeping the good information in some sense. We prune out the higher scattering frequencies, so large K values. We truncate these, which is considered a form of low pass filtering in the nonlinear Fourier domain. And the problem with doing this is that if you know anything about Fourier transforms of images, the Fourier transform of an image has the edges and fine details of the image encoded in the large frequencies, the high frequencies. So by removing the high frequency information from the scattering data, we are losing the edges and fine details of the image. So here in picture form, we have, this is the physical setup. It's a heart and lungs tank phantom setup. So we take measured data of this situation here. We can compute the scattering transform, which is just, it's a 2D function and it's got a real part and an imaginary part. So that's why we're seeing two plots there. And we're looking down on the function. So, you know, this is a surface, but we're looking down on it from above so we can see an image. And so you can see here these edges that are kind of snipped off. We have trimmed off the stuff that got kind of oscillatory, that blew up in the presence of noise. And we're trying to keep the good stuff that's, you know, closer to the origin. The origin is in the center of these plots. But it's the high frequency information on the outside that encoded all of the edges and fine details. So even though we couldn't keep that information because it had too much noise in it, now it's just completely gone, and we get a blurry image as a result. We've lost the edges and fine details in that image. So one of the things that I've worked on in recent years is improving the spatial resolution by replacing some of those high frequency scattering, you know, the high frequency components of the scattering transform, replacing those with a priori data. So if we know some approximate organ boundaries, maybe from a previous scan, we can assign guesses for conductivity values, and then we compute a stable a priori scattering transform from that. And we can take then the high frequency information from that a priori scattering transform and append it onto the outside of the scattering transform computed from the measured data. And we get this improved reconstruction with sharpened boundaries now. So here's a couple examples of the type of improvement that we can get from that. So you can see here, here's the original image, the tank photo. Here's the standard dbar reconstruction, and here's the improved reconstruction with the a priori data. And yeah, so it's a sharpening procedure. Here's some human data of the same kind of idea. So here is a previous CT scan of the patient that we use to extract a priori organ boundaries. And then we can take as many EIT scans as we want and just use those a priori boundaries from the one CT scan. So here's in this column some standard dbar reconstructions, and here's the corresponding a priori reconstructions with the extra information added in to sharpen the boundaries. Here's another project I've worked on recently. This was a joint project with the Colorado State University EIT lab and the EIT lab at the University of Sao Paulo in Brazil. We combined EIT data with ultrasound tomography data, and these are just numerical simulations right now. But here is an example of a ultrasound phantom, so a numerical phantom. Here is the standard ultrasound reconstruction, standard dbar reconstruction. So these are the types of images that we would get from the two different imaging modalities. But then we incorporate some EIT data into the ultrasound algorithm and some ultrasound data into the EIT algorithm. And you can see here, these are the resulting images from the combined modalities. So you can see that we do get some sharper information that more closely resembles the original phantom. And here's another one that I worked on recently, removing artifacts from EIT images. So we want to remove these artifacts that are these like bright pink areas. They don't belong in the images. So we did some nonlinear Fourier domain filtering and came up with these images with the artifacts removed. And this was a project I actually did with some students. And the most recent thing that I'm working on is using deep learning algorithms, machine learning, to extract a priori boundaries. So in the past, we've just kind of gone in when we want to extract organ boundaries, we click all the way around, these organ boundaries. It's very time consuming. You know, lots of human bias gets introduced in the process to generate the a priori boundaries. And so the idea is that if we have the scattering transforms computed from the measured data, maybe we can train an AI, a computer, to automatically generate organ boundaries that go with that scattering data. And a human can't do this. A human cannot look at these scattering transforms and say, oh yes, clearly that corresponds to, you know, these organ boundaries. But we're finding that we can train an artificial neural network to do it for us. So this is something I'm working on currently. So here's a little schematic of an artificial neural network. And the basic idea is that we put inputs into the network as the scattering transforms. Those inputs propagate through the network, and then the computer makes a prediction of what the organ boundaries look like corresponding to the real and imaginary parts of the scattering data. And so this is a project I'm working on right now with some students along with Colorado State University. And the results hopefully are coming very soon for that. We're making a lot of progress. It's very exciting. So that's about all I have for you today. So thank you very much for listening.
Thank you, Melody. It was a nice talk. So Thomas has to leave, and now I'm taking charge. So first, let me thank you for your talk, and I know that everybody enjoy. And if anybody has a question or comment, you can do it also in Spanish if you want. People are shy today.
That's okay.
So, Melody, I have a question. So, for applying this method, you need to do some simulation. So, you need a power computational system, no? So,
Yes.
how expensive it should be?
Yeah, so my computing needs are an ongoing issue, especially working at, you know, a school like Gonzaga, which maybe doesn't have the big bucks that some schools might for funding these things. But recently, for example, I was able to purchase, well, yeah, believe me, it was a long uphill battle, but I got a machine with a really good GPU, which can do the deep learning stuff. And it was on the order of $4,000. And, you know, that's probably the low end for what you would really want for something like this. You know, like more expensive is always better. So yeah, that's, I would say, you know, a good solid machine is on the order of a few $1,000s for this.
But
so.
in the program that you're using, I mean, the simulation, how long it takes to make the simulation?
So to actually like do some of the data simulation that we're doing, it doesn't take too long. The deep learning algorithms do take a little while. So the deep learning stuff right now, you know, like we'll run, you need to run what's called like 1,000 epochs of the algorithm to train the network. And that can, you know, take like, 15 hours on a, you know, like a good machine with a good GPU in it. And so if you have just a very basic, you know, laptop or something like that, you're just not going to be able to do it basically.
Mm-hmm.
And then, so that's like one time through the network. So you make your little adjustments to the network, like, oh, maybe I'll try this and this and this. And then you sit back and wait for, you know, a day for it to spit out some information for you. So
you have to be patient.
yes.
So there are some comments here. People saying great talk. Thank you, Melody. So, ¿alguien tiene alguna pregunta que quiera hacer? So if there is no more question, let's send the speaker again. And thank you, Melody. You are very welcome in our seminar. So this is the first non-Spanish speaker. So we are happy.
I'm honored.
Yeah. So thank you so much. And so we come back in 2 weeks. So thank you, Melody.
Thank you.
I'm going to stop.
Thank you too. Thank you.